What is going on, YouTube? This is Just Crust here, and I am back with another YouTube video, and today we are going to continue this channel's tradition of discussing a semester in review, and today we will be discussing my mathematics semester. In previous videos, I have mentioned that I am a double major in both mathematics and history, and so these will be separate videos talking about the classes that I have taken, specifically the classes I took last semester, how they went, how I thought about it, and then plans for the future, because I am getting to that time. I am about to be a senior in college. So this semester I took 3 math courses, which is a personal best, and it is a record that will stay, because I'm not doing any more than 1. I'm doing 1 next semester. But I took 3, and they were of varying difficulty and definitely varying amounts of enjoyment. So let's first start off with what I think was my favorite, and that is the history of mathematics. History of mathematics was actually also the first math graduate level course that I had taken within this university, and it was taught by a historian of mathematics. And it basically tracked, well, the history of mathematics for about 10,000 years or so. It started all the way back in prehistory when we started looking at artifacts such as, I think it's the Shango bone, that is just a bone with like tally marks on it, and we deciphered if it is right, or if it's numbers or not, all the way through to Babylonia, looking at different tablets written, as well as then Egyptian tablets, and then we discussed those and what made those unique, as well as it's very important in those specific periods to do something, or to try to not do reconstructive history, basically projecting what we know back then, because some people were looking at the clay tablets of Mesopotamia and saying that they knew algebra, they knew the Pythagorean theorem and everything, and you have to do some rational reconstruction. That's called rational reconstruction, actually, but we basically did an entire 2 classes talking about how rational reconstruction is bullshit and how we can't project our thoughts. But then we went to Greece, and Greece is where we spent a majority of the first part of the semester, because there's a lot. We covered the Euclid's Elements, we covered Archimedes' method, we covered the 3 Greek problems of antiquity, etc., etc. We heavily analyzed every mathematical source that we could find from there. And then that was pretty boring. A lot of our sources were primary sources, and I found Euclid's Elements and Archimedes' method, and about every other thing we had to read Nicomachus and stuff like that. Very boring, very difficult to read, because it's math and words. Our notation didn't get created. It wasn't formalized, and it wasn't standardized. Well, it was standardized for a long time, but we could say that the modern notation was created in the 1600s by like say Francois Viet, but so that means that all of the math up until that point is in words or shapes at best, stuff like that, which made Euclid's Elements, Archimedes' method, etc. very difficult to read, very difficult to kind of understand, and it made for a very not fun experience to read. But it was still interesting in general, which it's the one crossover event I'll get in these degrees. And then after that, we spent a little bit of time in the Middle East, and then we spent some time in medieval Europe, and then obviously we crest towards the Renaissance. And within the Renaissance, we get the flood of money, and the flood of mathematicians and people is doing active science. We talked about the Renaissance in terms of space, like Galileo and Kepler and such. And we talked about math, and we talked about the development of mathematics through them, as well as eventually Newton and Leibniz. And that's where we get into the development of what we know as modern mathematics, the development of the calculus, the development of modern algebra, the development and the rigorization of both of those. And that's where we stopped, was about the 20th century. We hit early 20th century discussing rigorization of calculus, such as, and this is just one of the many examples, such as looking at Dedekind cuts, and then we looked at the modern algebra, through the eyes as far back as Galois, into the rigorization by other figures like Gauss and such. My thoughts on that class, very interesting. One of the most interesting classes I've taken by far. It was super, I think the philosophical debate that we could have about when did math as we know it start? When did theory of number start? Is a very interesting one because, I mean, you can see all throughout Greek texts, they think of numbers only as parts of shapes, and that lasts for a very long time. And that actually, multiple times throughout the early teens, you can see that stunt development in mathematics because people are afraid to push past that geometric barrier the geometric barrier of entry that they've set using Euclid's elements in the first place as their basis. It was very interesting to see that early on, and then eventually to just read the different types of history, the different branches of mathematics, and the different ways that they discovered and attempted to formalize their research. Like reading about Euler, ridiculous. Reading about Leibniz and Newton was great because they didn't hate each other for like the majority of their life. Reading about fucking Galois, a revolutionary who died a day after he wrote his math, wicked. Absurd. Very interesting stuff. I just wish the primary sources that we read were better. The reading sucked, and that made the class suck. That, and we had a research project to do. I think this is just a little fun extra to talk about because this will be like a teaser almost of what I'll talk about in my history video, which is the projects I had to work on in those history classes. But I had to do a research rough draft, a research prospectus, and then a research paper itself. The prospectus was about 5 pages. The research paper, I think for mine, ended up being 17 pages, something like that. And mine, my professor said we could do anything in mathematics, history, anything at all. And so I chose to look at the history of music theory. So as far back as ancient Greece, as far back as Archytas and Aristotle to modern day. And I looked at how math and music theory were intertwined and where they converged and where they diverged, how different interpretations of music in general led to those splits. And so I looked, at music as both music theory as music, which is, versus music as math. Oops. Both, which were talked about by the Greeks, but they were more intertwined because music at that point was solely the study of proportion. And I looked at where there was a start of looking at music as theory that started going, like looking more than proportions, trying to make things sound good, like a composition of sorts, versus using the music as math. Which was like looking at planets and such. And so those branches took us throughout, medieval Europe into the Renaissance, where I can say the musical side of music theory was capitalized on things such as the development of counterpoint, where we can see that they're using these very in-depth comparisons of mathematical proportions to make things sound better. That's the study of math within music, is making these things sound better because they mathematically fit better. Their ratios are better. And I touched on, the ratios of perfect fifths to fourths, et cetera, because I have a music theory background. I'm not a musician, but I have a music theory background. And then on the other side, I looked at the music as math, pure math, which was the proportions. And that very easily got capitalized upon by Kepler getting his third law of planetary motion. He used the ratio of the distance between planets as harmonics and just studied it from there. And it was very wicked. I didn't explain it as well as I could have because the books were dense as hell. And 17th century writing is over my head, for math at least. And then I finished the paper by discussing some modern music applications, or modern mathematical applications in music theory, which are group theory and algebraic geometry. So I didn't touch on algebraic geometry. I saw it, I looked it up, I saw it in some papers and PowerPoint, and I literally fucking could not have left the website earlier. But the group theory that I found in math was very interesting, and I found very in-depth papers about it, and I covered the very small parts of it that I could understand, because I don't have a huge abstract algebra background. And it was basically just saying how you can relate the 12-tone equal temperament scale to the D12 group and do some funky group operations on D12, and you can get cool constructions of music, such as the circle of fifths, such as you can get any chord that you want, etc., etc., which I thought was very interesting. Paper was interesting to do, difficult to do, because I had to do a lot of primary source looking through, Greek writings, and then I had to do a lot of dense mathematical research papers that I also did not understand. So that was fun. And then the next class I'm going to discuss, I enjoyed still. These are still classes I enjoyed quite a bit, and it is what I would say dynamical systems and differential equations. And so dynamical systems and differential equations is my third differential equations course that I've taken in my mathematics career. It is the direction I like going the most when I'm in math. I like going the applied route. I could have, gone for applied math, but I didn't because I didn't know that was an option. But so in applied math, I've done my linear algebra, and now I've done ordinary differential equations, I've done partial differential equations, and now I've done dynamical systems. But what makes dynamical systems different? They're very weird. Instead of looking at how our system progresses over time, we are looking at how our system progresses in different spaces, and how we look at our curves and our systems and all that. And I could tell you a lot better if I remembered. That class was a fever dream. It was a lot. And so I'll just read from the textbook, the excerpt from the beginning of the textbook, because this is also going to be my basis to say what I actually learned. The major part of this book is devoted to a study of nonlinear systems of ordinary differential equations and dynamical systems. Since most nonlinear differential equations cannot be solved, this book focuses on the qualitative or geometrical theory of nonlinear systems of differential equations, originated by Henri Poincaré in his work on differential equations at the end of the 19th century, as well as on the functional properties inherent in the solution set of a system of nonlinear differential equations embodied in the more recent concepts of a dynamical system. Our primary goal is to describe the qualitative behavior of the solution set of a given system of differential equations, including the invariant sets, and limiting behavior of the dynamical system or flow defined by the system of differential equations. In order to achieve this goal, it is first necessary to develop the local theory of nonlinear systems. This is done in Chapter 2, which includes the fundamental local existence uniqueness theorem, the Hartmann-Grobman theorem, and the stable manifold theorem. These latter two theorems establish that the qualitative behavior of the solution set of a nonlinear system of ordinary differential equations near an equilibrium point is typically the same as the qualitative behavior of the solution set of the corresponding linearized system near the equilibrium point. If that didn't make sense to you, that's fine. It barely made sense to me. Let me just read some of the chapter titles that we had to learn. We went through all of Chapter 1, all of Chapter 2, and then a little bit of Chapter 3. So Chapter 1 is linear systems. That's going through just linear algebra. This is linear algebra. Chapter 1 is linear, but translating linear algebra into differential equations terms, basically. So, diagonalization, eigenvectors and eigenvalues, complex and otherwise. We learned how to take the exponential of an operator. We learned how to take the exponential of a matrix. And by that, you also have to learn Jordan forms and such. Chapter 2 is our nonlinear systems, so that was a lot of what the intro mentioned, such as, maximum interval of existence, the dependence on our initial conditions and parameters, stable manifold theorem, Hartmann-Grobman theorem, and then center manifold theorem, non-hyperbolic critical points in R2, etc., etc. And then Chapter 3, which was nonlinear systems global theory, only covered the first couple parts of that chapter, which were global existence theorems, limit sets and attractors, and I personally actually did a presentation on periodic orbits, limit cycles, and separatrix cycles. Could not tell me to repeat it because I don't remember any of it. But that's basically what we did. Can I explain any of that to you right now? No. Was it interesting? Absolutely. I thought it was very interesting. And what my professor obviously is an applied math person. He is obviously doing a lot of work in differential equations, specifically on the really big unsolved flow question. Um, and the name is stumping me. Give me 1 second. We are back. It is Navier-Stokes. We always looked at it as a dynamical system. We looked at dynamical systems in our book as well as other examples, and then these is ordinary. Our class was on ordinary differential equations. However, to show both higher level examples and more complicated in-depth examples, would translate this into Navier-Stokes, which was wicked, disgusting even, because I remember looking at Navier-Stokes and PDEs whenever he'd want to show that this stuff gets more complicated. The class was very interesting. The homework was pretty fun. The textbook itself, which was the big thing that I just read that long excerpt from, it is Dynamical Systems by Lawrence Perko. This shit sucks. This is an awful textbook. Very bad, actually. And my professor didn't agree with that, but he understood. A lot of it was very vague wording. It's a graduate level textbook. I didn't know that. And also required this entire course requires a background in real analysis that I just didn't have, because we're going to get to that in like a second. I decided to take these classes concurrently, and I at times definitely felt the repercussions of my actions. This class needed a deeper real analysis background than I had. It also needed a deeper linear background than I had, but I don't blame myself for that because I took the prereqs of linear. It's just I think the prereqs are wrong rather than I was wrong for not having the appropriate knowledge, because I've never learned the Jordan form before this, etc., etc. But that's a complaint for the school. That's not a complaint for the class itself. I didn't have the proper real analysis background, neither did a couple of my classmates, because they were also in my real analysis class. And the professor did a great job of acclimating us and defining things when necessary for both real analysis and differential equations, because he also, prereq for this class was not ordinary differential equations, because it's completely different. Solving them are completely different. So that was not a required course, so he would define even the most basic of things about differential equations, just in case type of a thing. And so it was very interesting. It was difficult to follow, but I think this is definitely one of the more applicable things. Like if you work in the sciences, I think differential equations, dynamical systems is very applicable in that world. I think it was very interesting, very fulfilling. And it would lead me to, if there was offered a graduate level PDE course, I would take it. If there's a graduate level course on dynamical systems, I would take that. I think it'd be very interesting. I wouldn't take it for a grade. I would not take it for a grade, but I would take it. I would audit it if I could, because I think it would just be a very fulfilling and interesting experience to learn more about the theory of, say, PDEs. But that's enough about the fun math classes. Again, I'm saying fun kind of loosely here. That's enough about the fun. So we're going to get to the third math class, which is real analysis. As I mentioned about 2 minutes ago, I did not have a real analysis background for dynamical systems because I was obtaining it at the same time. I took real analysis concurrently with these two other courses, and real analysis is frequently known as a weed-out course for a math major. It is the most difficult the most difficult basic proofwriting you will do. It tests your skills of proofwriting as well as your ability to understand the deeper concepts of things you might have already learned. I've taken Calc 1, I've taken Calc 2, I've even taken Calc 3. That was required of me, and now I'm learning why things worked. I learned how to prove IVT and MVT. I learned the definition of a derivative with epsilons and deltas. I learned continuity. I learned the convergence of a sequence of functions. I had to do a 45-minute presentation on the Weierstrass approximation theorem in a group. My part was like 15 minutes, but just approximating the convergence of sequences or of functions. I learned all of that. I had to write proofs on all of it. It sucked. This sucked. I think the difficulty of real analysis is opposite of the difficulty of abstract algebra, where abstract algebra is taking is just introducing a ton of new concepts to you in ways that you've never seen or heard. It's introducing new operations. It's introducing groups and fields and rings and all of that stuff at the same time. And while it's using things that we do know and we do understand at first, like natural numbers, the real numbers, the radicals, etc. It's using them in a completely foreign way. So it's all largely unknown, but still kind of surface level at first. That's my intro to abstract algebra was pretty surface level, and I still did not great in it. But that's one thing. And then real analysis is saying this is all the surface level stuff that you were taught. You already know the surface level. We're going to dig deeper, and we're going to try to get you to redefine everything you know. Because you can say what a derivative is. You can say that you know that pi is irrational. You can say that, oh, that is not continuous. I don't know why that word is tripping me up. Now you can say that that function isn't continuous or anything, but unless you can prove it rigorously 99% of the time using epsilons and deltas, it doesn't matter. Whereas in Calc 1, we took it for granted that this function has a discontinuity. We can see it on the graph. This function has no derivative. It has a corner, etc. Like, we took all those things for granted, and now we're going back and proving why they work, like IVT and MVT. I found the class very difficult and very boring. Very difficult. I can talk why it's boring because at the end of the day, that's preference. That's preference of content. I prefer applied mathematics. I prefer learning about PDEs. I enjoyed abstract algebra a little bit. I might do more of that in the future, but I like applied. So proofing is difficult for me. Proofing stuff that I have to remind myself that I can't just do the logical thing because that's not rigorous enough is super difficult. That's where I struggled early in abstract algebra. We were trying to prove literally -1 times x equals -x because it's so fundamentally elementary. I'm not saying that calculus is elementary, by the way, but that's so fundamentally elementary that it was difficult for me to break it down into super small, minute pieces to where I need to reverse engineer it, if that makes sense. And I felt the same types of difficulties at times in real analysis. The other times, I was just stupid. Math is hard, man, and I'm not great at it all the time. The concepts I felt were difficult, and they were boring, and I loved my professor. He was you could feel how excited he was to be able to teach real analysis. He loved analysis, and he was great, and he was bubbly, and he gave out jokes, and he made connections with the whole class, but it was still, at the end of the day, difficult and boring, and harshly graded too. But that's a lot. Those are a lot of personal preference things. I think there were some things, obviously, we had to skip for time. Because realistically speaking, in an analysis course, it's a lot more important if you know about the convergence of sequences and functions and the definition of the derivative, definition of the integral, rather than learning about in depth about metric spaces. I like metric spaces. I learned about metric spaces in dynamical systems. I have a good amount of experience with metric spaces. We have to literally everything in dynamical systems takes place within normed spaces, but I didn't learn that much about them in my real analysis class. And that was a major part of one of the chapters. And it's just the things we pick and chose that the things that we were given the privilege to pick and choose. I think you pick and chose the wrong ones, basically. But in general, real analysis is difficult, but I can see why it's crucial. I can see why it's important for the degree. And that's at the end of the day, that's fine. I can see why it was important for me to take it. Did I want to take it? No. Did I enjoy taking it? No. Would I take another analysis course? No. But I get why I had to. I get why I had to take that class more than I had to take dynamical systems, or why I had to take that more than history of math or something like that. So where do I go in the future with math? As I said, I'm a senior, I'm becoming a senior in college. Where do I go from here? I have one math course left for my whole degree, and it can be anything I want it to be. It can be an elective. And so I'm going to, as of right now, I'm going to take complex variables, which is basically just applying the complex plane. And I'm excited for it. I feel I've gotten a little taste of complexity in all three differential equations, actually. All three courses have mentioned the use of the complex plane. It's pretty interesting stuff. I don't know what it's talking about most of the time. All I know is Euler's formula, e to the I pi plus 1 equals 0, or whatever, that kind of thing. or is it eta? It's plus 1 or minus 1, one of the two. And I know that, and I know the sine formulas and the cosine formulas because we talked about that in history of mathematics actually, because again Euler did everything. But I'm excited for it. I think it'll be a good stopping point in my math career. I've done a ton of applied math, which in complex variables is applied math. I've done a ton of applied math, and I have a basis in theoretical math. I have a basis in abstract algebra, and I have a basis in real analysis. Do I want to continue that? No, I don't think I'm good enough. I don't think I'm good enough at math to be able to push forward to a graduate program. That's the honest truth. I won't say exactly what my GPA is, but like I know it's a good GPA, but it's not graduate program worthy. I don't think my analysis skills are graduate program worthy, and I don't think I have the desire to do a graduate program in math. No matter how much I find certain aspects of applied mathematics like partial differential equations and dynamical systems. I like both of those. I'm not going to say love. I like both of those. I don't think I could pursue it for 5 to 7 years. I don't think I could give that time. I don't think I could be strong enough in other fields of mathematics to pass qualifying exams for PhDs. So realistically, without auditing a class, I'm probably going to audit a class in math my spring semester because I won't have any math classes left. So I have a free spot. Will this be the end of my formal math education? Yes, it will. Am I happy about it? Kind of. There will, it's like, masochism kind of, or whatever, the one where you like the pain a little bit. It's like I complained about it, but I liked complaining about it. I'm gonna miss it a little bit. Will this be the end of my education in math in general? No, I will keep looking. I'll keep learning. I'm well connected in the online math community. I'm watching. I'm lurking. I'm reading. I'm always curious about what new to learn in math. I'll be Googling stuff. I'll be falling down the wiki holes all the time. I'm always reading specifically about the history of math, but I'm also reading about field theory and group theory and other number systems. And like I get to be more open with what I want to learn. And so obviously that won't give me the best depth or the best, it won't even retain because I'm not going to be doing work on it. But I will stay researching on my own time. I'll stay reading. And I think that's exciting. I'm excited to keep reading what I want to read. But it will be the end of my formal math education after the spring semester, hopefully, if I pass. Big ifs, still big ifs. We're not we're out of the woods, but we're not. The murderer is still in the sight. We're safe to a point, But that was my math. That's math. That's what happened in math last semester. It was a very impactful semester. A lot of things happened. A lot of awful mathematical things happened. But I took 3 math courses, which is great. I was proud of myself for finishing all 3 of them. I needed to, but I was still proud. That was math, and I'm happy. I'm happy where things are going. I'm happy to continue doing math. That's math. In another video, I'll talk about my history progress. I think there's a little bit more interesting stuff, if not a little bit less content actually to talk about. But until then, it's been Just Crust, and thank you all so much for watching.